What is short answer? The sum from k equals to 1 to infinity of kth harmonic number by k square x to the power k is Li3 of x minus Li3 of 1 minus x plus log 1 minus x Li2 1 minus x plus 1 by 2 log x log 1 minus x plus theta 3. Yeah, and this is a short answer, to be honest, like, because the sum involving harmonic numbers are even longer than this one as well, but this one is just 5 terms. Yeah, fine. And how do we deal with this problem? So basically we have a generating function for the kth harmonic number. Yeah, for the kth harmonic number we have a function f, which I will say later on. Now what you can do is you can first divide both of them by x. Yeah, we can divide both of them by x. Yeah, and now uh, this will just be sum of hk x to the power k minus 1, isn't it? Yeah, and now what we will do now is we will integrate this from, let's say, 0 to t, 0 to t. And now what does this gives us? Sum from hk x to the power k by k, isn't it? And this is from 0 to t, so that's why this will, at 0 this is just 0, at t this is t to the power k by k, isn't it? T to the power k by k, and there will be some again function, some function z. Yeah, and now you see we already have a k over here. Now what do we need to do? Again, divide by t. We can divide by t in both sides. Yeah, and that will make it t to the power k minus 1. Yeah, again do the same, integrate this from 0 to x. Yeah, and what does that give us? Sum of hk and then t to the power, now that will be x to the power k, x to the power k by k square, isn't it? So this is how we find this sum. This again, now let's say it will be h. This is how we are going to deal with. And now let me share the generating function of the normal harmonic number that I told in the first place. So the generating function for the harmonic number to the power p, to the not power, to the superscript p, this is actually equals to Lip of x by 1 minus x. Yeah, and now if this p is 1 for our case, just for the harmonic number, in that case as subscript k x to the power k, this will be equals to Li1 of x by 1 minus x, and what Li1 of x is minus ln of 1 minus x by 1 minus x. This is the function that we will use to find the answer. Yeah, this function already seems like kind of tougher to integral, but we will deal with this. Let's see how we will. Okay, so now we begin with this sum from k equals to 1 to infinity as k x to the power k. Yeah, we know this is minus ln of 1 minus x by 1 minus x. Now what do we do next? We divide by x. Yeah, and what does that give us? Okay, that gives us t to the power k minus 1. Yeah, and now let's make this x variables as t. Yeah, it doesn't really matter, so that later on we integrate from 0 to x, and that will be fun. That makes this x variable t. T 1 minus t 1 minus t and then t. Fine. Now let's integrate this from 0 to x. Yeah, from 0 to x. Now what do we get? Over here it's easy. Sum from k equals to 1 to infinity as k t to the x to the power k by k, isn't it? Now over here what do we get? For the firstly, what we can do is, we can use the partial fractions. This can break down into 1 by t plus 1 by 1 minus t dt. Yeah. And what can we do now after using partial fractions? Okay, so let's break this into two integrals. Integral from 0 to x minus ln of 1 minus t by t, again minus ln of 1 minus t by 1 minus t dt. Okay, now what can we do? This over here is just the definition of the Li2 function, Li2 of x. And this over here you can easily integrate. You can substitute u equals to ln of 1 minus t, and then minus 1 by 1 minus t dt, that will just be dy. So that's why this is ln square 1 minus t by 2. Yeah, y square by 2 basically. And this one is already from 0 to x. I have already evaluated this. Now for this one, the limit is again from 0 to x. So that will give us Li2 of x plus ln square 1 minus x by 2 minus ln square of 1, that's 0. So this is the answer for the integral from sum of k equals to 1 to infinity h of k x to the power k by k. Let's again write this in terms of t and then again integrate it from 0 to x like we did earlier. Sum from k equals to 1 to infinity h of k, if I divide by let's say t itself, t to the power k minus 1 by k, this is equal to Li2 of t by t, and then plus ln square 1 minus t by 2t, isn't it? Yeah. And now let's try to integrate this from 0 to x again. 0 to x again. Yeah, with dx. Now if we try to integrate this from 0 to x, this one is basically easy because this is just Li3 of x. Yeah, this is the definition. Basically we have that integral from 0 to x of Lip of x by x dx. This is actually L, okay, no, not x. Since here's x, here I need to use t. Yeah, Lip of t by t dt. We know that this is just Lip plus 1 of x. Yeah, so that's why, and this is Li3 of x, and then plus we have 1 by 2 times integral from 0 to x of ln square 1 minus t by t dt. Now we will deal with this integral individually because this one itself is in a trouble for us. Now this is just Li3 of x plus I, 1 by 2 times I is the answer. If now we need to find I. Yeah, so I is basically integral from 0 to 1 of ln square, not 1, x, I'm sorry, 0 to x of ln square 1 minus t by t dt. Now how do we deal with this? First thing will be to use integration by parts, because we know that the ln 1 minus t by t, this can be integrated. So we separate this from ln 1 minus t and we try to use integration by parts. So we will have I equals to basically ln of 1 minus t will be alone, and then we will have minus Li2 of t. Yeah, ln 1 minus t by t, that's integral is minus Li2 of t, and this is from 0 to x. Yeah, and then minus integral from 0 to x 1 by 1 minus t times minus 1, the derivative of ln 1 minus t, and the other integral is minus Li2 of t dt. Fine. Now I is basically ln 1 minus x and then Li2 of x Yeah, it's 0, both are 0, so that's 0. And also don't forget minus sign. Over here minus minus gets cancelled out, and minus integral from 0 to x of Li2 of t by 1 minus t dt. Now how do we simplify this? Basically you should always try to have just t in denominator, and that will be easier, because Li2 of 1 minus t can be easily like changed to Li2 of t using the Euler's reflection formula. Yeah, so it doesn't matter like if you have 1 minus t over here, but in your denominator always try to make just t. So we'll do that. Minus ln of 1 minus x Li2 of x minus, if I make a substitution u equals to 1 minus t, basically this will be 1, this will be 1 minus x, and there will be minus dt. So that's why we reflect the limits of integral from 1 minus x to 1, and Li2 of, since I'm making substitution that u equals to 1 minus t, our t will be 1 minus u. Li2 of 1 minus u by u du. Yeah, because I've written du, minus sign is already in action over here. Now how do we do? We can use Euler's reflection formula of polar logarithms to convert this to the Li2 of u. I equals to minus ln of 1 minus x Li2 of x, and then minus integral from minus 1 minus x to 1. Now this formula is basically Riemann zeta of 2 minus ln x ln 1 minus x minus Li2 of u. Yeah, that's the formula. So since there are such formulas, the integral becomes longer, but it's not tougher. The longer doesn't mean really tougher, yeah, because these are the same stuffs we are doing again and again, and that's making it long. Minus ln of 1 minus x Li2 of x. Now this is just minus Riemann zeta of 2 times ln of u, and from 1 minus x to 1, it 1, that is 0, minus ln 1 minus x, minus minus plus, so we get plus Riemann zeta of 2 times ln 1 minus x. Yeah, and then okay, how did I get x over here? That's clearly u. That just made me unhappy. Fine. Now we had integral from 0 to 1. This is ln of u ln of 1 minus u by u du. Yeah. And the last one is basically last one is simple, just plus Li3 of u from 1 minus x to 1. Yeah. Now we have to deal with this integral again, and now last one is simpler. Last one, let's deal with individuals now. Okay, let's deal with this individually. The last one is simple. This one is just Li3 of 1 minus Li3 of 1 minus x. Yeah, that's clearly easier. Now let's deal with this. We have, so that's what makes it somehow difficult, because there are a lot of things to deal with. But this one, I think we have already done this one in one of my previous videos as well. This is not a new thing. Okay, how do we deal with this? Basically we use integration by parts. So ln of u as it is, and the other one is just minus Li2 of u. Yeah, going from 0 to 1, minus integral from 0 to 1, this is 1 by u minus Li2 of u du. Yeah, and now this is 1, this is 0. Oh, is this really from 0 to 1? No, I don't think so. Okay, this is not from 0 to 1. Yeah. I'm sorry for messing this up again. This is from 1 minus x to 1. 1 minus x to 1. 1 minus x to 1, 1 minus x to 1, 1 minus x to 1. Fine. Now at 1 this is clearly 0, and then plus, that is ln of 1 minus x, because this minus was plus, and then li2 of 1 minus x, yeah, and then plus, this is li3 of u 1 minus x to 1. So this is ln 1 minus x, li2 of 1 minus x plus li3 of 1 minus li3 of 1 minus x. Yeah. So we solved that as well. Now let's combine all of them together. This integral becomes minus, sorry, let me use black again. Minus ln of 1 minus x li2 of x plus zeta of 2 ln of 1 minus x, and now this one is plus ln of 1 minus x li2 of 1 minus x. Do I notice something? Yeah, I do. And fine. And then okay, so there's plus li3 of 1 minus li3 of 1 minus x, and again the same thing is there, plus li3 of 1 minus li3 of 1 minus x. Yeah. Now this is the I, and to notice something, basically I can merge these two things, because Riemann zeta of 2 minus li2 of x will again have another simpler form in terms of li2 of 1 minus x. Yeah. So if we try to do that, if we try to merge these two, let me do this with some other pencils. Let's say green. Okay. So we try to merge these two. We will have ln of 1 minus x, Riemann zeta of 2 minus li2 of x. And now again using the Euler's reflection formula for pole logarithm function, Riemann zeta of 2 minus li2 of x, that is li2 of 1 minus x plus ln x ln 1 minus x. Yeah. Now using this we have ln 1 minus x li2 of 1 minus x plus ln x ln square 1 minus x. Yeah. And now from this, let's write the answer again. If we rewrite the answer again, we now have ln 1 minus x, and notice that okay, let me write it first and then I will say li2 of 1 minus x, and then plus ln x ln square 1 minus x. Yeah. Notice that this is the same term as this one, so we can write 2 over here, and then 2 li3 of 1 minus 2 li3 of 1 minus x. Okay, I think this is now the final I that we are looking for. Now after that we have I. We know that our answer was like way above, like over here. Yeah. This is like, so there are like so many parts, like the first part was there, second part is there, and it was itself in a part. So this Poiret logarithm dealing with this is like such a mess. So now this is li3 of x plus half of these things. Yeah, basically most of them have 2, so it will be easier. Ln of 1 minus x li2 of 1 minus x. Yeah, and half of this thing, half of ln x ln square 1 minus x and then Li3 of 1 is actually zeta of 3, zeta of 3 minus Li3 of 1 minus x. That is the answer. To write it properly, I can write it like this. Let's say Li3 of x minus Li3 of 1 minus x, and then this thing ln 1 minus x, Li2 of 1 minus x, and then 1 by 2 ln x ln square 1 minus x, and then plus zeta of 3. Yeah, Li3 of x minus Li3 of 1 minus x plus ln 1 minus x Li2 1 minus x plus 1 by 2 ln x ln square minus x plus zeta of 3. Let's see if this answer is correct or not. If we try to check if this answer is correct or not, we see that the answer is actually Li3 of x minus Li3 of 1 minus x plus ln 1 minus x Li2 1 minus x plus 1 by 2 ln x ln square 1 minus x plus zeta 3. Exactly the correct answer in the same order because I had memorized the order of the expressions. Yeah, and this is solved. Like this is the short answer, and this is way long. Yeah, not too long as well, but like just think like how long answers would be. Like there's a person, uh, Colonel Lone Balian, named as Colonel Lone Balian. Like he solves a lot of such problems, and the answers are like 10 times long, 12 times long. Like I just wonder like how does he manage all those. And this man is a really like a great person. Like he has uh, contributed a lot in the harmonic series SOMs. Yeah, and yeah, his papers are also wonderful. Do check those. Now let's talk about the flow of the problem. We first our idea was to just like divide by x and integrate. Yeah, and so we had this expression. We divided by x and integrated. Here we use the definition of Li2 of x, and here that was simple new substitution. And after that, over here again we divided by x and integrated. This one was simple, but this one was not that simple, and this one had a whole new journey. Now the first thing we did for this one was to use integration by parts. Yeah, and this one was simplified. Yeah, but over here again we got the expression where we had to. Okay, now this was too simple. Like if this had a simpler form, it would be solved over here itself. But now this simple looking expression made it tougher, because this simple expression, due to this we had to do all of these steps. Very bad. Now to simplify this, we had to make a number or just t in denominator, so we got this expression. Now this is the problem. We had to use the Euler subtraction formula, and such giant expressions were there, and we did. And this again, this gave us some problem to integrate, but we did. And others will also we are integrated. We integrated them, and yeah, this. And now we try to simplify this. This was not necessary. This was the answer itself, but I did anyways, and we got the expression finally. So that was it. That was the solution. Hope you enjoyed the video. Thanks for watching, and look forward to seeing the upcoming videos too.